Okay, so I think it's about time. So, hello everyone, good afternoon. Welcome to our YouTube session about AI agents and KG-driven NSAI and other relevant uh, AI technologies like large language models. Our theme is about driving innovation in geoscience data analysis. So, after you're checking in, we will start our agenda. Our session is arranged as follows. Firstly, we will have three presentations, each take 15 minutes. And after that, we will have around 30 minutes for three breakout rooms. For each of the group breakout rooms, we will have one of our speakers in that room and sharing their demos, and maybe you can play with some interactive demos in that breakout rooms. And after that, we will close all of the breakout room and gather everyone together in our main meeting room to answer some Q&A. And the highlight for our session is about leveraging advanced AI technologies to tackling geoscience data analysis works. And let me start with my presentation. Um, I hope everyone can see my screen. So it's okay, if we can, okay, thank you. So my presentation is in the name of Open Large Language Model and Geoscience Data Analysis Workflow. And we will apply this pipeline in our developed Open Minted data portal. And I will give the background for this later. So at the beginning, I would like to emphasize that the large language models mentioned in this presentation is not simply use them using with the website UI. Therefore, it's not something like you can chat with them and make them to answer your question, because that is a very straightforward usage for ChatGPT. But we would like to leverage the large language model in a much more in-depth level. Therefore, it can be leveraged in our geoscience data analysis pipeline more in a streamlined way. So beyond chat, we will use the large language models as tools. And we will also introduce some technologies to address the data cutoffs, because we all know that large language models are suffering from data cutoffs. They do have a broad memory and knowledge, but they are still have some time cutoff limitations. And in the end, we will leverage the large language models to show how convenient it can be for users who has maybe limited technology background, can also get their hands in large language models with science data in a very convenient way. So the object for the presentations is to provide the user-friendly data analysis UI, and we will leverage the large language model to tackle the multi-step task processing. And in addition, because the large language models showed in this presentation is not only the ChatGPT, we also apply fine-tuning to the open models to support the open science and open data analysis. We'll show the details later. So firstly, please allow me to briefly introduce the Mindat. Mindat is a very famous and maybe one of the largest mineral database in the world. It has been established in 2 decades ago and holds more than thousands or and millions of mineral data, and share them on the website like Wikipedia, so everyone can browse the website through as they want. But recently we decided that we should develop a data API to leverage to streamline the experience for the users to access to the mineral data through their mineral database more efficiently. Therefore, they can download the batch mineral data from the website and in a very convenient way. But we very quickly we realized that people from geoscience communities who are not that comfortable doing so many complex programming to interact with our API. So there are some voice to ask us to simplify the process to access the open metadata, i.e. the mineral data from the website. So here is our a preliminary result. You can see that we can use the large language model to tackle this kind of request, say, show me the pyrite record from Mindat, and here is the AI response from our ChatGPT model. And in the backend, you can see that this is not simply answering the question through their built-in knowledge. It did has a equipped with a tool to access the Mindat search to search for the request data and answering with the uh, data set you just downloaded, so you can answer it with a more reliable result. And but based on that initial result, we quickly upscaled the large language model workflow with Mindat to this kind of architecture. You can see the user in Blue Node is representing a human user, and the supervisor is a central large language model. You will play the supervisor role in this workflow, and after it receives the user input in natural language, it will decide which tool it should take to tackle that request. And as a result, you can see after the construction of that large language model driven data analysis workflow, our workflow can directly taking in the user requests in a very complex sentence and understand the underlying request. And here is the final output. And you can see this is the detailed happening in the backend. After user come up with a certain request, the supervisor agent, which is a large language model, ChatGPT 4.0 in our experiment, it will thinking that, okay, so the user need to plot the network for the element distribution. So you should firstly asking the collector agent to retrieve the dataset. Then with the dataset in hand, you should plot the request network using the dataset just downloaded. And after finish the dataset downloading and plotting, it will decide it automatically that I've already fulfilled the user request, so I can return the result to the user. This entire workflow is fully automatic. No further interactions needed. Human user only need to come up with certain requests, and it will end up with the beautiful visualizations. And in addition to the network, this is what happening in the backend. You can see it goes 2 rounds of tool asking. After receiving the user request, it will ask the collector to do the data downloading task and asking the plotter to plot the visualization. And in addition to the mineral distribution network, our workflow architecture can be easy to scale up to tackle up further tasks in the same workflow. I will show this feature in the demo later. And you can see this is another human request asking for the mineral heat map for Brazil. And this is the result for that certain country. And by changing the keywords in the question, and actually you can rephrase this question whatever format you want. But if the semantic is explicit and ChatGPT-4 can understand your question, you can end up with identical results. And the workflow presented in the previous slides are based on the OpenAI. Well, even if it's called OpenAI, the ChatGPT 4 model is not open sourced. So it's a commercial model, so we have to pay for the API quota to use their service. And as a result, if you're trying to publish your large language model-based service, it will result in a ridiculous bill if you got plenty of users. And in addition, their service is online, therefore you may also suffering from the service outage, which has happened several times a year in 2024. And it's a commercial model, so if your workflow is tackling with some not yet published data, you might feel uncomfortable about some privacy risks. So in my third experiment, I'm trying to migrate this entire workflow to the open models. And in this study, I used the Llama 3.1 from Meta company. You can see compared with the ChatGPT 4.0, the parameters and the size are extremely small, which makes this model uh, runnable on your local machine. So this Llama 3.1 model and the workflow based on this open model, I can run on my personal laptop with only 16 gigabytes of memory. And this is what happened. Because you can see, compared with the parameters, the reduced size of parameter and the model size can extremely affect the performance of the open model. So we do need to have apply some heavy fine-tuning or retraining for to our open models. Therefore, to improve the performance and even matching the performance of commercial models like ChatGPT-4. So this is the entire pipeline we applied to retrain our open model. You can see we start with a human seed task set, with which are some human handwritten input and output pairs. And we applied the prompt instruction strategy to ask the ChatGPT-4 mini to mimic, to refer to this template and generate more training data for our fine-tuning. So our initial seed task is only arranged around 60 questions. And after this AI-assisted generation, we end up with more than 2,000 of training questions of expected input and output for our large language model-driven data analysis workflow. And after fine-tuning, we applied the fine-tuning tiny open model. You remember it's only around 5 gigabytes of the model size to the exactly identical workflow to answer or to conduct the user request about mineral data visualization or heat map creation. And this is what happened in our training data generation. And I can share more details in the breakout rooms later. And as a result, we end up with more than 2,000 training set, and with the fine-tuning parameters experiment setting like this. This is what we got in the end. And you can refer to the next slides. You can see that our fine-tuned model, which is around 100 times smaller than ChatGPT 4.0, can achieve the best overall performance in our testing set. And for for the ongoing case, the performance is quite comparable to the commercial models. So as conclusion, the fine-tuned large language models are can achieve comparable performance to the commercial models, and we end up with conclusion that we can use the open models to conduct efficient and cost-effective approach for large model fine-tuning, and the result of the large model architecture is scalable. And well, due to the time limitation, this is what I got right now. And in during our breakout rooms, I can show you the demo and you can play with it. And the link to this demo can be found in our notebook. You just check in. You can find it in the resources for this session. And see you in our breakout rooms. I will give the floor to Wei for his second presentation.
Yeah, thanks, Jing. Hello, everyone.
Oh,
My name is.
I'm sorry,
Mhm.
Wei. Can you try swap the display?
Okay, I just saw it. My mistake. Yeah. Hello, everyone. Good afternoon. My name is Weiding Chen, and I'm from University of Idaho. And I'm so excited to introduce our work about the integrating neurosymbolic AI and knowledge graph from enhanced geochemical prediction in copper deposit. Let's dive in. Accurate mineral prediction is critical for resource exploration and environmental sustainability. And the traditional approach, including the geological mapping and geochemical analysis, it just rely on extensive fieldwork and expert interpretation. And USGS has done a lot of fieldwork. And the traditional machine learning methods, it can automate data analysis and improve accuracy, but it just operate like a black box. So it got its limitations. For example, it is heavily data driven, a lack of interpretability, and it is limited integration of domain knowledge. So let me introduce our approach with neurosymbolic AI. And neurosymbolic AI is combining both symbolic reasoning and deep learning, but we have tried deep learning in our study since our task is to predict the mineral deposit type in our study. And the deep learning model is perform not that good as the machine learning model. So we just use machine learning model here, and we combine large language model, knowledge graph, and machine learning. Our goal is to enhance accuracy and then improve the model's interpretability and leverage domain expertise into our approach. And first, we should generate a knowledge graph and use the knowledge graph to extract the symbolic rules and use the rules to guide the machine learning models with these rules. Yeah. There are three major components in our approach. The first thing is the data collection and pre-processing, including clean and normalized geochemical data, label data using geological rules. The second part is the knowledge graph construction. We extract the rules from literature using large language model and validate with domain expertise. The third part is the knowledge-infused machine learning model. We use knowledge graph to guide the machine learning training and prediction. And we choose random forest as the machine learning model here because we combine like multiple models. And random forest is the best one. And we can see that from the graph, first, just the empirical data, and the raw data after cleaning and normalized, just use the machine learning model of the random forest to train it, and we got the target class 1. Then after we generate the knowledge graph, we add domain knowledge. We just use the rule integration, and then we train the second model, which is the rule guide neurosymbolic AI model as target class 2. The difference between the difference between model 2 and model 3 is that we add more rules to make it like an extend the rule guide neurosymbolic AI model as model 3. That is the evaluation and interpretability. So where is our data from? Our data is from the geochemical dataset from the USGS. Yeah, this is the maybe not the only one, but it's the most clearness figure I can find from the USGS dataset, the website. It includes data for various copper deposit, and it includes geochemical concentrates like copper, iron, and sulfide. How we do the data cleaning work is first we remove the duplicate, correct outline, and handle missing value. Then we filter it to extract porphyry, copper, Mothian AU data. Because there are more than 400,000 of records in the raw data. And after we group by deposit type, which we got the copper deposit, there is around like 20,000. Yeah, deposit type. And here is some examples of the deposit types. Then we just building the knowledge graph. The rules we extract is from a book named Mineral Deposit Models, written by Coase and Singer in 1986. Here is an example in the books, like porphyry copper deposit has high copper and Mothian concentrate with quartz veining. And we use ChatGPT 4.0 for summarizing and extracting structural knowledge from geological text. Because if we just do it by ourselves, it just time consuming and it needs so many time to do it. And let me just, here is an example of the scar copper deposit. Because I can't show the entire knowledge graph here because it's hard to visualize. Just take a copper deposit as an example. We can see it has some elements like iron, like copper. It has some minerals like this ones, and it has this kind of rock type. And we also can see its associated deposit like porphyry, like skarn deposit. Our next part is enhance the machine learning with domain knowledge. So the first part, we just got our knowledge graph. Then we just trying to extract the rules from the knowledge graph. So the rule-based feature just add binary indicator for deposit-specific patterns. And here's an example, like porphyry copper, Mothian has high copper, and scar has iron-rich scargillum, and it has these elements. And it also make the rules as a concentrate to incorporate rules as during the model training to align predictions with geological principles. In this way, we got benefits that we got improved the prediction accuracy for underrepresented graph and enhanced interpretabilities. So we just, as I mentioned before, we just compare three kinds of models. The model one is a baseline random forest. The second one is a rule guide random forest. The model three is an extended rule guide random forest. And we just use these key metrics to evaluate our performance. First one is accuracy. It is overall prediction correctness. And then there's the percentage, is the ability to minimize false positive. And the recall rate is ability to correctly identify accurate positive case. And the last one is F1 score. So here is the result of the three models. First, we see the accuracy. Model 2 and Model 3, the accuracy of test and validation is just a little bit higher than the original Model 1. And the average F1 score of it just also a little bit higher. But the the main point here is that about the recall rate of the minority class, such as the highest sulfidation deposit, it just the validation recall is from 0.25 to 0.50. And of others like this one, the baseline model just can't recognize this kind of deposit type. Only the Model 3, which add that specific kind of rules, can recognize that, but it's just not that correct. Just a little bit higher than this Model 1 and Model 2. So the highlight here is that the extended rule guide machine learning model achieved the highest accuracy and recall. The minority classes show significant improvement, and we adjust the challenge of minority class prediction. We use sharp value to get the key predictor identified, which is the feature importance. We can see as Model 1, just the raw data. It just rely on raw geochemical data, such as uranium and copper. And our Model 2 and Model 3, we can see the knowledge uranium ppm. And such kind of, the knowledge is the kind of features that we just input by the rule guide methods, that we can use the rule guide methods to know how much our rules affect the model and guide the model. And the takeaway is that the integration of rules just enhanced the feature significance. There are also limitations and challenges here that we faced. The first one is the rule quality dependencies. Our model much relies on the accuracy of manual create rules, and potential gaps of ambiguous in geological knowledge. The rules can affect the model in like, if the rule is wrong, then it may guide the model to the chaos, and is perform much worse than the original model. Yeah, and the second one is computational complexity. Is embedding symbolic rules increase resource demand, because we have to first check the rules, if the rules is right, if the rules can be applied to our model. And the last one is the adaptability. Is the state rules may struggle with evolving geological insight, because the deposit type may change, and this kind of one kind of deposit type may be recognized as another kind of deposit type as the time went. Yeah. And our future work is to help us to address the limitation and the challenges. The first one is meta knowledge graph integration. It's just to develop metadata knowledge graph to guide the construction of dynamic adaptable knowledge graph. The second one is the automation to leverage local large language model to automate rules generation from domain literature. Just I will cooperate with Jing, as he just moved his model from ChatGPT 4.0 to his local large language model. The third one is the user accessibility to create a user-friendly workflow for broader adoption. And the last one is apply neurosymbolic AI to other geoscientific challenges. For example, mineral exploration, because this test is kind of simple, and this is the reason why the machine learning model just perform better than the deep learning model. But if we are using this method to the mineral exploration field, it's just much harder task, and we will apply the neurosymbolic AI like the symbolic reasoning with deep learning models, like convolutional neural network, to do a much complex task. And here is the key findings. The extended rule guide NSAI achieved 99.16% validation accuracy. And the interpretability, it can embedding expert validation rules and using sharp values made prediction transparent, aligning with geological principles. And the key geological features are drive the model success. The last one is NSAI AI balance computation efficiencies with expert geological reasoning, voice charts, and reliability in mineral predictions. And I also got a demo about the newest polygon and logic graph. There are 3 steps. We can access the Colab notebook, follow the guide step to load data, visualize the knowledge graph, and run the newest polygon model. Then we can explore the results and evaluation provided within the notebook. And here is my presentation, and thank you for your attention. Zifu, you can go with your presentation.
Right. Thank you, Willing. I'll share the screen here. Right. I hope everyone can see my screen here. Hello, everyone. My name is Zifu Wang. I'm from George Mason University. I'm a PhD candidate under Dr. Chao Weiyang's guidance. Today, I'm very happy to share some interesting findings from us on how did we optimizing the context-based location extraction by tuning the open source large language model with the RAG. So I think most of us getting the data from the media when we do the NLP tasks. This media can include social media or news media. So in this project, we're actually using some news media which contains embedded geographic information. Those information including description of locations, regions, and movement patterns that may be extracted to analyze associated events or phenomena. So those geographic information plays a very important role in understanding the evolution of associated events or trends, or other different scenarios across temporal and spatial dimensions, especially in the times of crisis, such as armed conflict, like ongoing Sudan conflict right now, which is also the research use case of this study. Therefore, the ability to extract accurate spatial temporal information from media data is very important for tracking the spread and the impact of those kind of crises. However, this information is often complex, as the location details are frequently embedded with broader contextual elements. The context-based location include not only place name, but also more detailed geographic entities, such as neighborhoods, landmarks like harbors or mountains, or directional terms such as easterns. Additionally, locations are often integrated with temporal elements such as dates and times, and the single article may contain multiple locations and various type of temporal data. Moreover, to facilitate further analysis based on the extracted location data, it is very crucial to extract the data into a well-structured format to reduce effort needed for data cleaning after the extraction. So there are a lot of traditional natural language processing tools that we can use, such as name entity recognition. However, there are some shortages of natural language for the name entity recognition that we have facing. Basically, cannot address very well for the complexity of a news data set. Right now, the large language model demonstrates some capabilities in various NLP tasks, such as location extraction, which is this task what we need. But there are still some challenges in accurately extracting complex and multi-entity location description. For example, in what we are currently studying in the Sudan conflict, a single news article may reference several incidents in different dates and locations. And the simple prompt tuning method sometimes struggle to produce the required structured output. What do I mean by required output? Required structured output, I'll explain it later. Basically the answer from the large language model always with inconsistency and hallucinations. So with the recent introduced retrieval augmented generation, which is RAG, we used the article related to Sudan conflict as a use case. We target to have the following three objectives. First is to improve the accuracy of the context-based location extraction. Second is try to compare the RAG performance against the traditional name entity recognition and also prompt tuning strategies, and also compare the performance of different open source large language models. So we reviewed several name entity recognition works in recent years. We still feel often fall short of recognizing more detailed location information, such as neighborhood name, that were not included in their dictionary, as well as understanding the complex relationship between the extracted location and associated context. Additionally, some of the framework rely heavily on manually input toponyms and their spatial context prior to extractions, limiting their generalizability to less structured address or those contain ambiguous geographic information. So right now, we also read some literatures about large language model. However, those large language model, although they can extract the location, but regular prompt tuning strategy often fall short of achieving full span matching. So when I say full span matching, it's like when we ask the large language model to output specific address, neighborhood, state, country, and the date. We want it in this kind of structure. It cannot will perform. Basically, it will perform with inconsistency. Sometimes language model with those simple prompt tuning strategies also output unnecessary information such as explanations alongside the extracted locations, which cannot be directly used for further analysis, and we need extra cleaning for the human interventions. And then, so we want to implement RAG to reduce this hallucination further to comparing to the regular prompt tuning strategies. And lastly, we want to see how different open source model performs so that we can help researchers to reduce the cost of using large language model. So based on all those literatures, the current challenges towards context-based location extraction from the text includes first, identify complex multi-identity location descriptions and their associated thematic elements. It's very difficult in a required format for further automatic processing with high accuracy. The regular prompt tuning method often falls short, which require human interventions to clean and validate the generated information. As I list the example over here and previously, in the context of current Sudan conflict, a single news article may reference several incidents with different dates and locations. When GPT model were tasked with extracting information in fixed formats such as neighborhood, state, country, and date, from the news content, they often generate additional unnecessary explanations. And third is that we want to investigate how RAG can improve the accuracy of the context-based location extraction. And lastly is investigate how different open source models perform. So we can reduce the cost comparing to using the closed source large language model, such as ChatGPT. So the data used in this study compresses the details of news report of the conflict incident that occurred in Sudan between April and September of 2024. These reports were gathered from various reliable sources and all those sources actually got cross-validated by several domain experts. And eventually we got 377 incident to test this very different method on various large language models. So this is an example of the data, one of the data entry. So we have many attributes over there. One of the most important role is the incident narratives, which is describing what's happening in certain date and what happened in those kind of student conflict. So this is a methodology map we're having. So we first collect data from the incident log and then comparing name entity recognition, zero shot, instruction-based prompt tuning, and also RAG. And in the name entity recognition, we just use Python packages to directly extract it, and also for the zero shot and also the instruction-based tuning, we just use prompt tuning. And for the RAG, we implemented the vector database, which is phase developed by Meta, so that we eventually use different models to test it, which include Meta, Mistral, Gemma, and Qwen. And lastly, is the hyperparameter tuning. Eventually, we get evaluation from precision recall and F-score. So in the name entity recognition, we use SPICY and the GeoPy to analyze the geospatial labels of each word entity in incident narrative cells. If a word entity is identified by SPICY with label GPE, LOC, or DATE, they will be extracted. So basically, GPE, which is called geopolitical entity, refers to countries, cities, states, or other political regions, while LOC, which is locations, refers to physical locations that were not political entities such as mountains, rivers, or general geographic features. And date, oh, sorry about that. And the date refers to any recognized date or date-like expression in the text. So once all those relevant information extracted, GPE and also LOC entity are passed to GeoPy package to determine the city and the state and country information. And all date information will be output as a stream in the format of neighborhood, state, country, and date. So in this template, the system prompt instruct the model to generate the location and the date of each incident described in the news article. So in the user prompt, the content from the incident narratives will serve as the input with the expectation that large language model will output only with the required format with neighborhood, state, country, and the date, which is month, date, and year. And this is the instructional-based prompting we're having. So in this system prompt, where for this prompt tuning method, the large language model specifically instructed to produce outputs according to the required format, ensure that they understood what information to provide and what to exclude. So the prompt template is showing as below, which is over here. In this template, the formatting include the instruction for the formatting the extracted geographic location and dates based on the response schema outline, which is over here. And the input represents the incident narrative cell contains the news articles about Sudan conflict, and the output is just to generate a response. So it is important to note that in different prompt description, we want to minimize the difference in the prompt description, so to ensure a fair comparison between zero-shot and instructional-based prompt method. So with the RAG implementation, the whole process of implementing RAG involved utilizing phase. It's a vector database tool developed by Meta. This process began by inputting the context-based news articles. They first converted into numerical vectors. So these vectors capture the semantic content and also structural information of the article, and they are stored in a fast database. The same input of the user query will be converted into, the same input will be converted into the different numerical vectors when processed by different large language models, as each model is trained by unique corpus. which affects the numerical representations of words and the relationship between them. When a user query is submitted as a prompt, it is also processed with the same embedding model to retrieve the relevant information from the vector database. By using the vectorized news articles retrieved along with the prompt, the large language model is fine-tuned to extract the geographic information from each article. It is important to know that the same prompt is used as in the zero-shot prompting to evaluate how much RAG can improve the location extraction. So five specific hyperparameters were selected for tuning process: model variance, model sizes, temperatures, context limit, and maximal tokens. Model variance represent different large language model architecture developed by various organizations, such as GIMA developed by Google, Llama developed by Meta, and Mistral developed by Mistral Q, and developed by Alibaba. And each unique so each of them has a unique training corpus and objectives. So model example. And another example is the another parameter is the model sizes, which is for example, when we have the Llama 3.1, we both selected 70B and 7B. As a dash after the model name is indicate the size of the model parameters in billions. So in theory, a model with more parameters offers better performance, particularly in tasks requiring understanding or complex reasonings. And the third parameter is the temperature. Temperature controls the randomness of the large language model output during the text generation. A higher temperature increases the randomness, producing more creative or varied response, while a lower temperature generates more fact output. Since this is a context-based location extraction which requires precise information, we believe that a lower temperature is generally more effective as it reduces the variability and enhance the accuracy of location extraction. Last two we tested is the context limit and also maximal token. Basically, context limit defines the maximum amount of input text, and the maximal token sets the limit on the token of number that large language model can generate. Those two, we tested different numbers. Eventually, we decided to set them up in a fixed number because in this kind of situation, we don't require it to generate in a long paragraph, which we just need a structured answer. And those text input in the news normally will not cross 8,000 tokens. So we decided to set it up. Although we tested different parameters, eventually we decided to make them fixed as the context limit as 8,000 and maximal token as -1, which is the maximal. To evaluate the performance for various methods to extracting the context-based location from news article, we implemented a manual evaluation system because we believe in order to reduce the hallucination, a manual verification is very necessary to see how the large language model is performed. So a comprehensive scoring, a comprehensive scoring system was developed to quantify the performance, focusing on the 4 key components: date, locations, state, and countries. Each correctly identified component contribute equally. So with each component worth 1 point, resulting in a total possible of 4 points per incident. So if the response did not adhere to the specific schema, for example, presenting a paragraph instead of presenting the required structure format, will automatically assign it to a 0. Because I think this step actually is very crucial that output fully match the prompt requirement to ensure that automatic data processing without human intervention. Especially, we are targeting to use this data for the future analysis for our own research. As I said before, the large language model expected to output as the neighborhood, state, country, and date. For each incident, if the large language model generate unnecessary information, such as explanation and reasoning, we also give a 0 too. So as this additional content introduces noises and also requires further human effort to clean. So this, after the performance score is manually calculated, we use them to determine the recall precision F1 score. So recall is calculated by dividing the total correct point earned by the maximum possible point from manual annotation, and also so to minimize the impact of random variation or outliers, each method actually is tested multiple times under the same hyperparameter settings and with the same large language model. Same as the recall score is then averaged across different multiple round of the testing. Same as precision is calculated by dividing the total correct points earned by the maximum possible points from all results produced by the model. Similarly, the precision score is averaged across different articles through multiple rounds of testing. And lastly, is the F1 score, which is harmonic means of the precision recall, which can only be high when both precision and recall are high. So come to the result. When we have the traditional natural language, traditional name entity recognition performance, it only has around 50, 34, and 40% for each evaluation scenarios. So there are some limitations, especially significant limitation in meeting our requirement is that they fail to extract the terms like Sudan unless the exact term was explicitly mentioned in the text. Even if the related entities such as Sudanese liberation movement were referenced, they cannot find Sudan over here. And also they struggle to interpret the relationship between the dates and locations in context. And also frequently when they extract irrelevant phrase such as a second consecutive day or that day instead of correctly identify the actual date. Lastly is that the format is an issue. They often produce disjoint output like North Delta Friday or Alcaba May 10, rather than a coherent extraction like what we expected, like Al Fisher, North Delta, and then Sudan May 10. And this is the result for our zero-shot prompting. So overall, GMAT2 9B actually has a overall highest precision recall and F1 score across different temperatures over here compared to other models. Sorry, I misclicked. And also Llama 3B, 7B consistently perform better than 3.1B, and also the QN and Mistral did not perform that well in this case. So, the limitations on zero shot we find out is that they always fail to accurately extract the date, even though they were explicitly mentioned in the text. So one example we have is over here is that on May 2nd something happened, and the model produced output like they actually find the neighborhood, then state and country correct, but they do not give a right date over here. And also they struggle to generate with the required format. For example, the response are like neighborhood, the argument, state, Khartoum, country, Sudan, and the date is May 3rd, which is deviated from the specified format given to the model. And also the format issue were even worse when the model output response in paragraphs from rather than in an order list, often including unnecessary heading and subheadings. And this is the final output of the instruction-based prompting. So in this one, it actually performed worse than the zero shot. But from our evaluation, overall result actually went. We think it's better, but from our evaluation process, it went bad because there are several problems we had. Is that while the data and location they were actually re-extracted very correctly, like this one over here, they have a good date and good location. But they produced additional explanations, which is not required and distracted from the overall response quality. So this kind of thing actually happened a lot in our during our evaluation. Like although they have those information extracted correctly, but over here they do not perform well. And lastly, the second problem we got is that it struggled to identify multiple locations within the same article, also resulting in a lower overall success rate for those instances.
I'm sorry, I have to interrupt. We have already 10 minutes past the time, so can we wrap up in minutes?
Sure. Yeah. So sorry for taking too long. So this is the result of RAG, and then we can see that RAG actually handled the complex query involving multiple locations within the same graph, and it can have a consistent format. So have a comparison over here. This is an article example, and the instructional based prompting answers like this, which only has one location. But over here in the RAG, we have multiple locations with an accurate date. So this is the overall result. There are some interesting findings that we find that RAG can significantly improve the overall F1 score from 5% to 30%, depends on the different models and different different prompt method. And also in most models, lower temperature such as 0 and 0.1 tends to improve higher F1 score for specific for geographic location extraction. And overall, GEMA2 9B actually achieved the best score. And while larger model requires more running time, it doesn't necessarily translate to a higher accuracy. And our future studies will continue to investigate how to improve the RAG, how to improve the accuracy over there. And these study findings can be applied to other areas of research, which requires automatic location, such as automatic mapping, which is our next step for research. And this is a reference. Thank you for listening. Sharing.
Yeah. Thank you, Zifu, and thank to our audience, reaching to the end. And now we're going to have a 30 minutes of breakout rooms. And during this breakout rooms section, we're going to have 3 speakers separated in each rooms. There will be 3 breakout rooms, and we will show demos, and you can feel free to play with the demo and ask questions to the speakers. And that will be all of our raised agenda. And Aaron, can you help give us the breakout rooms?
Yep. So if you look toward the bottom, I believe in most, if you have the application, there should be a breakout rooms button. Click in that and you should be able to join one of 3 breakout rooms. So
Yes, I
jump
see
in there and let me know if you have any issues.
Okay, I'm going to join it.
All right. See you later.
And I'll hang out here.
I think we are pretty much coming to the end of our session. Does anyone has any further questions, or we are going to end this session in 2 minutes? Seems everyone is good.
Just wanted to say thank you for putting on the session. This was all 3 of the demos were really, really cool. I'm glad I got to see them.
Thank you. So if anyone has any further questions or would like to discuss into more details, feel free to contact us. We do provide our email address in the shared doc. So feel free to reach out. And thank you everyone for attending our session. Thank you for your interest. Thank you for your time. And hopefully we will also attend the E6 July meeting this year and provide subsequent research outputs. If you got interest, we can meet together in the E6 July meeting this year. And thank you, Aaron.